Hi everyone, welcome back to the channel. If you've been hearing the buzz about autonomous agents and wondering how they actually differ from the traditional AI models we've used for years, today's episode is for you. I'll break down the technical differences, practical trade-offs, and real-world use cases so you can decide which approach fits your project. Stick around until the end. I'll share a simple decision checklist and a demo concept you can try in under an hour. Let's go! Quick overview on what we'll cover. First, a concise definition of each approach. Then, architecture and training differences. Next, key capabilities and limitations. A few real-world examples and a conceptual demo. And finally, a practical decision framework. I'll keep this technical but accessible. Think of it as a guide for engineers, product managers, or curious developers. So what do I mean by traditional AI models? I'm referring to models trained for a specific task. Image classifiers, regression models, or even large language models used as single-call services. They take input, compute, and return output, often in a feed-forward or single-turn manner. Training regimes include supervised learning, unsupervised pre-training, and sometimes RL for fine-tuning. They're powerful for well-scoped problems and predictable pipelines. Autonomous agents, on the other hand, are systems that perceive an environment, set goals, plan, act, and iterate over time, often across multiple steps and interactions. They can call tools or external APIs, maintain memory, perform planning, and adapt dynamically. Agents are built to achieve objectives in an environment, not just map an input to an output. Let's summarize the core differences in plain language. Traditional models are single-shot or stateless. Input goes in, output comes out. Agents are stateful and action-driven. They maintain context, plan over multiple steps, and can call tools. Training focuses differ. Traditional models optimize for task-specific metrics, while agents often combine learning with planning, search, or symbolic reasoning. And importantly, deployment patterns differ. Agents orchestrate multiple components. Traditional models are usually a single inference endpoint. Diving deeper into architecture, an autonomous agent often includes perception, sensors or input parsing, memory, episodic and long-term, a planner or policy module, a tool interface layer, and a feedback loop for monitoring. Traditional models typically have a data preprocessing step, a core model, and a prediction endpoint. When building agents, you'll handle orchestration, state management, prompt engineering for LLM-based components, and safety constraints. Training and learning strategies differ too. Traditional models rely heavily on supervised datasets or unsupervised pre-training, followed by fine-tuning. Agents often combine reinforcement learning, imitation learning, heuristic planning, and episodic experience replay. For LLM-based agents, you might fine-tune the language model or use prompt-based reasoning with external memory and reward models to guide behavior. Okay, where do each shine? Traditional AI is great for classification, detection, forecasting, and single-shot generation tasks. Think image recognition, sentiment analysis, or translation. Autonomous agents excel in tasks requiring multi-step problem-solving or persistent action. Autonomous robots, virtual assistants that manage calendars and emails, automated research agents that search, validate, and synthesize information, or multi-agent simulations for logistics. Let's walk through a simple demo concept you can prototype: an email triage agent. The components: an LLM for language understanding, a memory to store user preferences, a planner to decide actions, reply, schedule, summarize, and connectors to the email API. Step 1. Parse incoming messages. Step 2. Classify priority and intent. Step 3. Plan and execute actions, then log the outcome. This demo highlights agent orchestration, tool usage, and iterative refinement. Quick pros and cons. Traditional models are simpler to train, validate, and deploy. They're predictable and easier to scale, but they can struggle with open-ended tasks and multi-step objectives. Agents are more flexible and powerful for complex workflows, but they introduce complexity. State management, safety and alignment challenges, harder to debug behavior, and higher integration effort. Cost-wise, agents can be more expensive at runtime due to orchestration and multiple model tool calls. Here's a quick decision framework. If your problem is single-step, well-defined, and performance can be measured with clear labels, go traditional. If you need multi-step reasoning, tool use, or persistent goals across time, consider agents. Also weigh constraints, timeline, budget, explainability requirements, and safety. For many products, a hybrid approach works best. A strong traditional model for core tasks and an agent layer for orchestration or edge cases. Looking forward, expect more modular agent frameworks, better safety tooling, and tighter integrations between LLMs, symbolic planners, and RL. Research is moving towards scalable memory, emergent multi-agent coordination, and cost-efficient orchestration. If you want to learn more, I'll link resources in the description. Research papers, open-source agent frameworks, and practical tutorials to build the email triage demo. That's a wrap. Autonomous agents aren't a replacement for traditional AI models. They're a different architectural approach tailored to multi-step, goal-driven tasks. Use the decision checklist we discussed. Start with simple prototypes and iterate. If you found this useful, like, subscribe, and hit the bell. And tell me in the comments which demo you want me to build next. The Email Triage Agent with an Autonomous Data Analyst. Links to resources are below. Thanks for watching. See you in the next one.